So I will talk about the first presentation is about the experimental efficiency of FRP bars as injected anchors for masonry structures. This is a work that I did together with Francesca Ceroni, which is from University of Naples, Partenope. So the other University of Naples, we are from Ludovico the second, and then with Alberto Balsamo, which is also from our university. So let's go a step back. Let's introduce the problem. And as you know, Italy is a very prone to seismic action country. So our problem is, in general, when seismic happens, that we have very, very large and severe damage on masonry buildings due to the fact that in several cases the connection between the orthogonal walls is lacking, is completely missing in several cases, and in this case we have this kind of mechanism, which means the simple overtuning of the facade. While when there is a little bit of a connection, we can have the compound overtuning. In each case, there is a very, very high vulnerability of masonry buildings against seismic action, and that's why we need to do something in order to avoid this kind of mechanism. So traditional solutions are mainly steel tie, the use of steel ties, that is very, very common in Italy and in general in seismic areas, or the use of RC or steel confining elements. But what we are looking at is the use of injected anchors that traditionally can be made by using steel rebars, and the idea is obviously to connect two orthogonal walls in order to avoid the overtuning of masonry. It is a very, very good solution, as clearly demonstrated by this picture. This is Amatrice, which is a little municipality in the central part of Italy, which was completely devastated by the earthquake in 2016. And as you can see clearly here, this was the core of the municipality. But one of the few buildings which remained, which stayed and did not collapse was this one. And you can see that they have already, they was finishing to do injected anchors, and at the end, the building achieved the so-called box behavior, and then obviously the damage was the unemployed damage, as clearly demonstrated by the diagonal cracks. So the solution is good, and it works, and this was demonstrated in field, which is the most important test. But now we are looking at how we can move, how we can use this solution by replacing steel, which is obviously a traditional solution, but has a very high problems in terms of corrosion. And this is a typical problem that we can find in masonry when we apply steel injections, because especially when we use tough masonry, this could accelerate the corrosion, and then the cracks can generate. So the idea is to replace steel by using FRP bars, which gives us much more high attest and high corrosion resistance, and in this way they can be really a sound alternative. So what we did, we started to look at this potential solution just in 2016, when we decided to test a full-scale member, so two walls, very poorly connected, as you can see here in our lab, and we applied gravity loads and horizontal loads in order to simulate the earthquake, and we decided to compare the behavior of the specimen without any kind of central solution and by using injections made by FRP bars. So to be fast and quickly, this is the result that we obtained during the test on the as-built specimen. As you can see here, we are plotting the horizontal force versus the drift, which is the horizontal displacement divided by the height. And here, the red line and the orange line represents the theoretical force at which mechanism 1 and mechanism 2 can happen. Obviously, since we had a poor connection, the capacity of the member was in between the two mechanisms. Then we stopped the test. You can see here the cracks at the interface between the two walls, and we decided to try to investigate on the effectiveness of a new solution, which was in 2006 the use of a carbo tube, which can be seen here, injected in this way, but in order to increase the bond between the injection and the masonry, we used this carbo tube with this carbon hollow tube with a stainless steel fabrics, which was wrapped around the tube in order to improve and increase the bond and avoid that the solution could be not effective. So we did the test, and at the end, when we did this kind of intervention, the new behavior is this one, reported in the green line, and you can clearly see how much the capacity increased. We obviously, strongly overcame the capacity predicted by mechanism 2, but in general, what we can say is that the failure moved from cracks at the interface, and we had no cracks anymore, and we had a rocking mechanism, demonstrating that the solution was really effective, and we had a very high strength and ductility capacity increase. So this was done in the past. Now what we are looking for, we are trying to understand, okay, the solution is effective, it's a sound solution, it can work, but now we need to provide some reliable design formulation in order to understand how much is the pull-out force that we can use in our calculation in order to be sure that practitioners can design this kind of solution. So what we did in these years was, first of all, literature analysis, and what we have a lot of a lot of theoretical formulation, which are mainly calibrated on steel rebars. And so what we need to do now is to try to understand how much this formulation can be applied when we replace steel with FRP. Generally speaking, the pull-out force depends on several factors, which are the type of rebar, the type of surface treatment, the embedded length, the masonry quality, and the injection mortar quality, and so on. And depending on all these parameters, we can attain different kind of failures. The red one here is the cone masonry detachment. Then there is the probability to attain the slippage between bar and grout interface, or between the grout and the masonry interface, called here CMD, SBG, and SGM, and then we can also attain a mixed failure mode. So, what we are working on now is to define and to carry out several experimental tests in order to evaluate how much is the pull-out force in case of FRP rebars. This is our test setup. We decided to test a specimen made by 3 blocks, made by tuff or other type of masonry blocks. The embedded length was 25 centimeters, and then you can see here an important aspect in our experimental program, which was the confining pressure, which was provided by using this device in order to exactly simulate what happens in a building when there is the gravity load in this direction and the pull-out force in this orthogonal direction. So we had a confinement pressure of 0.4 megapascal simulating the gravity action on the masonry. So now I will give you try to summarize the results of 2 rounds of tests that we have done in these years. The first one, which was performed some years ago, and you can find the details in this paper. We decided to investigate on the effectiveness of several solutions. First of all, we decided to use as a reference ribbed steel rebar, because the theoretical formulation are mainly based on steel. Then we used GFRP rebars, smooth carbon FRP rebars. The diameters were 12 and 10. And then we decided to replicate the surface treatment that we used in the preliminary experimental validation. So at the end we had 15 masonry prisms and 5 types of anchors: steel, glass rebars with or without surface treatment, and then hollow protruded smooth carbon FRP with and without the surface treatment. And here you can see the failure modes that were attained during the tests. On the left side you can see a green box showing us that this kind of failure was attained, which means the slippage at bar grout interface, and this was due to the fact that the bond was not so good. While when we look at the performance of rebars with a surface treatment, we can move throughout these other two kind of failure modes, which are the gliding at grout masonry interface or the cone detachment, as you can see here. In this slide, I tried to give you an overview of our experimental results. Here you can see the specimen labels. It means the material, which is masonry. Then we have the bar type, steel, glass, or carbon, and then the diameter, and then the surface treatment, and we have three types: ribbed, treated, or untreated, with the stainless reinforcement that have shown you before. The black curves are the 3 repetitions made on steel rebar, while the green ones are related to GFRP, and the orange and red ones to CFRP. Treated and untreated, orange and red, or green, these two kinds of green. As you can see here, comparing the force, slip, displacement, when we compare the performance of these rebars with steel, we can say that a good behavior can be attained when the treatment of the surface is done, which means that in these cases the behavior is similar to that of steel or even better, while without this kind of surface treatment, the results are less significant than those attained on the steel rebar. And here you can see in this table the final values of the pull-out forces and the average values, and how much without or with the treatment we had different results with respect to steel. So without treatment we lose 40% of the pull-out force, while in the second case we were able to attain more or less the same value, or even in case of the carbon solution plus the treatment, which was the same solution used in the full-scale specimen, we were able to attain a pull-out force even greater than that achieved on the steel rebar. Then, now, since our final goal is to calibrate a theoretical formulation, we decided to enlarge our experimental test program, so we have a round 2, and now we are looking at the performance of other kind of rebars. This is basalt rebars with the diameter 8, and then carbon smooth. The basalt has an helicoidal ribbed wrapping, as you can see here, and then again glass, diameter 10 and 12, with another different type of surface, which is an helicoidal wrapping, and finally a new solution, which was investigated in this round of tests, that is the use of a glass spike with a sand coating. And you can see this is the original spike, which then can be realized in this way. So again, we tested all the materials. I have no time to give you all the details about the material properties. I want just to show you that we did all the tests on masonry, mortar joints, and injections. And very quickly, moving close to the conclusions, these are the results that we obtained. This is the GFRP rebar's behavior, 10 millimeters diameter and 12. And you can see here the failure modes. Have to tell that in this case the masonry quality was a little bit poorer than in the previous round of tests, and this was the reason why we had in most cases mixed failure modes. But it is interesting to see that after the peak on GFRP bars we had a quite sinusoidal trend, which was due to the fact that there was a progressive slippage between bar and grout, and then obviously this resulted also in a reduction of the bended length. So this was the behavior which was recorded by the tests. And then it is also interesting to note that moving from 10 to 12 millimeters, the load increase was not so high as the area increase. So the load increased by a factor of 16%, while the area increased by a factor by a larger factor. Moving to basalt, you can see here that the rebed basalt bar performed quite well. We had a very force which was greater than before. So the highest value of tensile stress was achieved. And also there was a good behavior after the peak. So there was a residual bond giving us ductility. While in case of carbon bar 10, this is another surface treatment, but it was smooth. We had no so good results in terms of load, and this is because obviously the bond play an important role. Finally, the glass spike that we tested was really surprising because it gave a good result both in terms of pull-out force and also in terms of ductility, but the most important fact was that it was attained, in this case, the highest ratio between the maximum stress in the rebar and the maximum stress related to the capacity of the rebar. So here in this table, you can see the capacity, the ultimate stress capacity of each rebar, and the one achieved during the test, and this is the ratio, and you can see that by using this kind of solution, we attained a very high value, which is 0.4. So we exploited almost the capacity, much more, almost 2 times the capacity of the rebar with respect to the other solution. So these are the the conclusive remarks of this second round of tests. I don't want to repeat again all the conclusion related to the behavior of these rebars, while I want to spend my last 30 seconds to give an insight about the design formulation. As I told you, there is no formulation for FRP, so what we have done was to collect all the results available in literature on steel rebars and FRP rebars. Here you can see our experimental point, and we tried to define a unique relationship, which is not depending on the type of failure, just one theoretical formulation which can be used to evaluate how much is the theoretical pull-out force, and then we will move throughout the Eurocode approach in order to pass from the experimental value to the design value by using a reduction factor which is reported here. Obviously, we need more data, and so we expect to enlarge our test results to refine this design formulation. And this was my last slide.
Thank you.